We have already introduced Green's theorem. Let's recall what it says. So suppose we have a simple closed curve that cuts out a domain D. Its interior. It's oriented in the counterclockwise orientation, and it's denoted by partial of D. Then if we have a vector field which is continuous, differentiable actually on the curve and its interior, then the vector line integral of this vector field along T, along the boundary of T, is equal to the double integral of this expression that involves the derivatives, the partial derivatives of the components of the vector field in the interior of T. And today we would like to see how this can be extended, generalized, and used in different contexts. Last time we actually used it uniquely, exclusively, in this direction. So we wanted to compute a vector line integral, and we expressed this, we translated by means of Green's theorem the vector line integral into a double integral and proceeded to compute the double integral, which was a much simpler task than that of computing the vector line integral. So the first thing that we would like to do today is the following. So qualitatively, if we look at this integral, we can argue that it represents the total projection of the vector field onto the boundary in directions that are tangential to the boundary. There is a different vector line integral that gives us the amount of the vector field that flows through the boundary when the boundary is actually oriented with the outer normal. So you look at the boundary, you think of the direction that leaves the domain as the positive direction. You ask what amount of this vector field is flowing through that direction. So it turns out that the integral that gives that is precisely this. And this integral is known as the flux integral, or rather the flux of the vector field PQ through the boundary of D. And now the interesting thing is that we can still apply Green's theorem. We just have to be careful a little with the roles that each of these functions plays. So our role P would have been what is sitting right here. So this is the old P referenced in Green's theorem. And the old Q is what is sitting right here. So what are we supposed to do? We're supposed to take the old Q and differentiate it with respect to x and subtract from it the derivative of the old P with respect to y. So this becomes P sub x plus Q sub y, which is a new expression, which we call the divergence of PQ. And it also has a vector expression, which is similar to that of the curl. Instead of the cross product, we use the dot product. So if we call this the divergence of the vector field F being P comma Q, then this can be defined as the gradient operator dot with the vector field itself. So formally speaking, the gradient operator is an operator that can be written in vector form, and it has the partial differentiations as its components. And if we dot this with the vector field PQ, then what we're going to get amounts to multiplying the differentiation with respect to x by p, which means differentiate p with respect to x plus q with respect to y. And that's what we get. So if we put, and of course, a remark that we should make here is that the divergence of a vector field can be defined in all directions, unlike the curl that the way we defined it, at least, is valid only for direction for dimension 3. I'm sorry, for all dimensions, I mean. So we get the flux form of Green's theorem. According to which the flux integral of a vector field through the boundary, so this will be p dy minus q dx, is equal to the double integral of the divergence of the vector field, meaning p sub x plus q sub y in the interior of the domain D. Now, here one could be easily led into misconstruing this as a different form of Green's theorem. And pretty much it should be immediately clarified that it's pretty much mathematically the same formula. The same formula with different roles. So if you take the first formula, for example, which is known as the circulation form of Green's theorem, then if you replace P by negative Q and Q by P, then you obtain the flux form. So it's not something that has to be proven separately. And as far as the memorization of the formula itself is concerned, the only thing that one should know is really what the flux integral, the flux of a vector field through the boundary of a domain is. That is, one should know that the flux in 2 dimensions is defined this way. Once you know that the flux is defined this way, then you can apply the traditional Green's theorem, or just know that this integral is equal to the double integral of the divergence. So let's do an example to see how this whole business could materialize in a simple context. So as an example, compute, and even though we've already mentioned it, let's say this is the outer flux of the vector field F is equal to x squared y plus x, y cubed x squared plus y through the boundary of 0, 1 cross 0, 1. And here, the solution to this problem is going to be as follows. So if we denote this by P and this by Q, then we can say by the flux form of Green's theorem, it suffices to compute the double integral over 0, 1 cross 0, 1 of P sub x plus Q sub y dA, which of course will become a double iterated integral. And what is the divergence here? So differentiate p with respect to x, and that will give you 2xy plus 1. Differentiate q with respect to y, and that will give you 3y squared x squared plus 1. And now you need to integrate this whole thing. This is a very, very simple integration. Anyhow, let's do it in stages. So let's integrate first with respect to x. So that will give us x squared y plus x plus x cubed y squared plus x from 0 to 1. And this will give y plus 1 plus y squared plus 1 from 0 to 1 with respect to y. And obviously this will be 1/2 plus 1 plus 1/3 plus 1. So this is 2 plus 5 over 6. So this is, I guess, something like 17 over 6 if we clear denominators. I hope I'm not making any numerical error here. So I didn't even write explicitly the flux form of Green's theorem. I just said that by the flux form, the flux integral is equal to the integral of the divergence, and that gave us the computation. Now, another thing that we should say about Green's theorem is that it can be applied to much more general domains. So far, we have really looked at these very, very simple domains where we cut out a simply connected domain by as the interior of some curve. But one could have actually interior boundaries too. So look at this domain here. Take something like an annulus, for example. You could still apply Green's theorem here, but you have two boundaries, an inner one and an outer one. So when you try to apply Green's theorem here, you will have to orient those boundaries in the appropriate way. The outer boundary is going to be oriented in the clockwise, in the counterclockwise way, and the inner boundary in the clockwise way. Now, one might argue, is there any uniform empirical way that we can describe that unifies the two orientations? And it's what we mentioned in our last lecture, that if we sit upright on the plane and, on the boundary, then the correct orientation is if the domain lies on our left hand. So if you're on the outer boundary, then you have to be looking into the counterclockwise way in order to have the domain on your left hand. If you do it on the inner boundary, then you will have to look at the clockwise way in order to have the domain on your left hand. And please understand that it's possible to actually have a much more complicated domains than this, that have boundaries that consist of many components. So let's say that our domain is this interior, and we have these three holes. Then the boundary, which consists of 4 components, should be oriented like this. So this should be counterclockwise, like so, and this 3 should be clockwise. And when we take the integral has to be taken as a sum of 4 independent integrals on each of these curves with a corresponding orientation. This actually has to be studied more in the context of homology theory and much fancier theories that could be discussed in the context of a Calc 3 course. But let's turn to something else. We have already mentioned that our treatment of Green's theorem is going to be 95% from the vector line integral to the double integral, which leaves a 5% for the other way around. And it's not like we will have a very general way of using it, but we will have a very specific application. So in particular, if we have the following situation, so imagine that you have a domain that is cut off by a simple closed curve. So this is the domain D. And you consider the following vector line integral, very specific vector line integral, x dy minus y dx along the boundary when that is oriented in the counterclockwise way. Then by Green's theorem, here I don't even need to reference the flux form of Green's theorem. This could be my P, this could be my Q. Then Q sub x minus P sub y ends up being exactly 1 minus negative 1, which is 2. So this will be the double integral of 2 over the interior, where of course we can take 2 outside the integration sign. And since we're integrating now the function on, that gives us the area of D. And we come up with the following formula that the area of D is equal to 1/2 times this vector line integral. And please understand that one could find different vector line integrals. It's just that the specific one gives very agreeable integrations, as we're going to see. Now, the interesting thing is that what we have on the right, on the left, is the information about the area of a region, and on the right we have information that depends only on the boundary of that region, and that's very, very impressive. Not only that, but remember that behind every integral, one could consider appropriate Riemann sums in order to carry out the integration, at least to approximate the value of the integral. So imagine that we could have an instrument that internally could actually compute such Riemann sums of this differential form that wouldn't be too complicated to do. After all, it's just some linear functions that take part in it. If that was possible, then we would have an instrument that we could use in order to measure areas of very irregular or very general domains, for that matter. And there is such an instrument, which is called planimeter. And this is why I like to call this formula, this is not a standard nomenclature, the planimeter formula, because it has to do with the particular instrument. Now, if you think in terms of Green's theorem, then you can understand that this formula goes from the double integral, which represents the area, to the vector line integral, and that's why I refer to it as a formula that uses Green's theorem in the opposite direction. Let's do a simple example, and maybe another one which is not so simple. So let's start by computing the area of the ellipse. So compute the area of the ellipse with boundary x squared over a squared plus y squared over b squared is equal to 1. Now, what we should do here is it suffices, I'm saying what we should do, it suffices to compute the vector line integral of 1/2 times the vector line integral of this expression. And these, of course, the boundary of D is given by this. Now, this is a vector line integral. And certainly the vector field behind it is not conservative. And now one would say, should we go through Green's theorem? And the answer is absolutely not, because we obtain this integral by having applied Green's theorem. It's not going to be any good if we reapply it and pretty much go back to the fact that this represents the area of D. So if we wish to apply this integral, we have to go specifically with a parameterization, meaning with a mere definition of the integral. That's exactly the idea, that we started with a double integral, which was the area. We want to express this using a vector line integral, so we have to stay within the context of vector line integrals. And since this is not a conservative vector field, the underlying vector field is not conservative, we should just go with the parameterization. So how does one parameterize this ellipse? Parameterization of this ellipse is given by r of t is equal to a cosine t, comma b sine t, and t here should be between 0 and 2 pi. And what is the underlying vector field? F of xy will be minus y comma x. And if we take f of r of t, then that should be minus b sine t, comma a cosine t. And finally, if we take r prime of t, then this is going to be minus a sine t, b cosine t. So eventually, what is the integrand that we want to create here? It's f of r of t dot r prime of t, which is minus b sine t, a cosine t, dot with minus a sine t, b cosine t, and this is going to be pretty much ab sine square of t plus ab cosine square of t. And eventually we should take the integral of 1/2 from 0 to 2 pi of ab dt. And this will give us simply pi ab, which is a very nice generalization for the formula pi r squared, which is the area of the disk. Okay, but let's do something much fancier. Let's take advantage of the situation here, and let's put it this way. So find the area of the region in the first quadrant enclosed by xy is equal to x squared plus y squared squared. It's actually it's not as fancy as it may look in terms of what the shape is here. So I will just make an attempt to draw it where in the first quadrant, so it pretty much generically it looks like this. And what I would like to do is pretty much compute 1/2 of the vector line integral of the form that of the vector field that we described before. So x dy minus y dx along this curve C, which will give me, of course, what is going on, what the area of the interior would be. So the big question here, if we are to follow what we did in our previous example, is how do you find the parameterization for this? Now, this is not that straightforward, and we're going to use a very, very interesting parameterization. We're going to parameterize by the slope of the lines that intersects this curve. So we start with lines that start from the x-axis, and little by little we move this line, and we see that it intersects the curve at exactly one point, and the parameter that we use in order to describe those points that traverse those lines is the slope of these lines. And the slope of such a line, of course, is given by y is equal to, is given within the equation y is equal to tx. So this is the equation of a line for a t that lies between what? So t here is simply greater than or equal to 0. And less than infinity, if you like, because the slopes of this line start from 0 for the horizontal line and go all the way to infinity as you go to the vertical line. Now, here we would have to work in the way that we did before formally, but we're going to bypass this. And there is a really beautiful way of resolving this that is using, in some sense, the differential forms. Now, the interesting thing is that we have been calling these integrals vector line integrals. The truth is, something like this that appears here is a differential form. And in the context of a Euclidean space, those can be identified with the corresponding vector fields. This identification is not something trivial or something to be taken lightheartedly. However, it is possible. So we could ask how this differential form can be transformed for this particular parameterization. And here, the interesting thing is that there's a kind of product rule. So what we have is that dy is d of the product of two quantities, and we have that in such a case, it's t times d of the one quantity plus x times d of the other quantity. And now what happens is when we multiply by x, so x dy is going to be xt dx plus x squared dt, and xt or tx is what we called y, right? So now if you ask, and this is what creates the real magic with this choice of a vector field or of differential form to integrate, that this will become y dx plus x squared dt minus y dx, and you have this very interesting cancellation, and pretty much you have this form. So all you need to focus on is this, which means that you need to express x in terms of t. And how do you express x or rather x squared in terms of t? So this is where finally we have to go back to our original equation. And we're going to take y's tx. So this will be x squared t. And this will be x squared plus t squared x squared squared. And this will be x squared t being equal to x to the fourth times 1 plus t squared squared, which when we cancel the x squares, that will give us an x squared on the left equals to t over 1 plus t squared squared. So a lot of very unusual and interesting manipulations. The bottom line is that we got an expression for x squared, which is exactly what we needed, because that's what we're supposed to integrate. So it all boils down to this. You have 1/2 times the integral of this form right here, which is x squared, but x squared is known to be t over 1 plus t squared squared tt. And now the final act in this drama is what are the limits? We gave the limits right here. We said that they really go from 0 to infinity, which is really interesting because we get an improper integral. And now with a simple substitution, u being equal to 1 plus t squared, this will give us to u is equal to 2t dt, and t dt is 1/2 du. And so this will be 1/4 the integral of du over u squared. Right now, we have to be careful with the limits of integration. We have to plug them into the original, into the substitution. So if we plug in 0 into the substitution, we get 1. If we plug in infinity, we at least formally get infinity. The antiderivative of u squared of 1 over u squared is negative 1 over u. So we're going to get negative 1/4 times 1 over u. And we have to go from 1 to infinity. Of course, when we say plug in infinity, we really take the limit of 1 over u as u tends to infinity, which is 0. And if we plug in 1, we get 1/4. It's negative 1/4, which means that the final answer becomes 1/4. And that's it. That's the area. And that's a very, very unusual computation that gives you a completely different angle for these vector line integrals that we have encountered so far. It also gives you a very unusual parameterization, one that we haven't encountered before. In some sense, it gives you an instance of how interesting parameterizations can be out there, far beyond the ones that we have mentioned and that we're routinely using. This was a quite exotic example, and if you look at it, it uses pretty much everything you've seen in your calculus career, including Calc 1, Calc 2, Calc 3, with all sorts of differentiation tricks, integrations, improper integrals, substitutions, not to mention the planimeter formula and Green's theorem. So one of the most wonderful examples that one can encounter in an elementary calculus course. And that completes our treatment of the Green's theorem. Thanks for watching.